Welcome to Mrs. Z's Chemistry. This is the second lesson of our acid-base chapter. There are two different kinds of acids and bases. There are strong acids and bases, and there are weak acids and bases. Strong acids completely dissociate in water. So this A is representing any anion, whether it's a single element anion or a polyatomic ion. Acids donate a hydrogen, and so when the hydrogen is transferred to the water molecule, these are the products. We're left with A- and H3O+. In a strong acid, all of the H's leave the anion and turn into H3O. So all of the reactants turn into products. And there are no more HA left in the solution. This is a completion reaction because we say that strong acids are completely dissociated in water. Weak acids only dissociate partially in water. So the A still represents any anion, and the acid still transfers to the water molecule, and so the products look the same, A- and H3O. But this arrow is a reversible reaction arrow. The reaction can go both ways. As the reactants begin to react together and turn into products, they don't get to go to completion. So not all of the reactants turn into products. Some of the products begin to turn back into reactants. This is also called a equilibrium reaction. And these equilibrium reactions are often reactant-favored reactions, meaning in the solution we have all four of these species or compounds in the same beaker altogether, but most of it exists as the reactants, as the HA, or whatever the weak acid is, and the water. And very few of the acids lose the hydrogen and turn into A-. So that is a weak acid. The weak acids only partially dissociate. So in this section 14.2 and in the next one, 14.3, we will be focusing on strong acids and strong bases, but in the next couple of sections after that, we'll look at the weak acids and weak bases. So there are 7 strong acids, and they are listed on your periodic table. We have hydrochloric acid, and then hydrobromic acid, hydroiodic, nitric acid, chloric acid, perchloric acid, and sulfuric acid. All of these 7 acids, they all lose the hydrogen ion completely. They completely dissociate in water. If you do not have an acid that is on this list, then that means you know the acid is a weak acid in the problem that you're looking at. All right, so 14.2 is talking about autoionization of water. In pure water, some of the water molecules will act as an acid and some of them act as a base. As we've seen, water is amphiprotic, meaning it could act as either an acid or a base, meaning it could either donate a hydrogen or accept a hydrogen. So in between two water molecules, one of the water molecules might transfer hydrogen over to the other one, and then we'd have H3O and OH-. Notice that the arrow here is a reversible reaction arrow. This is an equilibrium system where most of the what you have in the solution is water molecules actually, and very few turn into H3O and OH-. This is referred to as autoionization. Auto meaning like automatic, it's happening just automatically, and ionization, well, they're becoming ions. Some of the water molecules become H3O or OH-, which are ions. So this is an equilibrium reaction, this autoionization of water. So let's look at an equilibrium expression. This is the concentration of the aqueous products divided by the concentration of the aqueous reactants. And this solves for something called the K, or equilibrium constant. This constant tells us how much of the reactants turn into products. Since in these reactions, these equilibrium reactions, not all of the reactants get to turn into products, we need to know, well, how much turns into products? Every equilibrium reaction has a different threshold or level of products that is produced. And so you take the concentration or the aqueous products, multiply them together, and divide that by the reactants that were multiplied together. Whenever you have a substance in brackets, that means the concentration of whatever is inside the brackets. And the concentration is molarity, as we've seen, which is moles over liters. So let's look at the equilibrium expression for this water reaction. We need to take the products over the reactants. However, here's one interesting key fact here. You cannot include liquids or solids in the equilibrium expression, only aqueous substances. If you had gaseous in these reactions, you could include gas as well, but in these acid-base reactions, we only have aqueous and then sometimes liquid or solid. So since we're not including the liquids, we only have products. And so therefore, we only have a numerator in our equilibrium expression. So the equilibrium constant, instead of putting a C for concentration, we often put a W for water. So this is often called the KW. And this value, KW, in any solution, not just pure water, but in any solution, it is 1 times 10 to the negative 14. This is specifically at 25 degrees Celsius. In this course, we are only going to look at problems that are at 25 degrees Celsius, but later on you might learn that at different temperatures, the equilibrium constant, meaning this K value, will change for the different reactions at different temperatures. Either warmer or colder will increase or decrease that K value. But for right now, for this class, we're only looking at 25 degrees Celsius. So let's look at this problem here. The concentration of hydroxide, or OH minus, in solution is found to be 1.4 times 10 to the negative 11 molarity at 25 degrees Celsius. What is the concentration of H3O plus? The fact that it says at 25 degrees Celsius, you can ignore that part essentially, since there is no part in the equation to plug in for temperature. We just know that the K value, the KW, is equal to 1 times 10 to the negative 14. That K value is also equal to the H3O concentration times the hydroxide concentration. Since we are given the hydroxide concentration as 1.4 times 10 to the negative 11, we can take our K value, the 1 times 10 to the negative 14, divide by OH, which is the 1.4 times 10 to the negative 11, and that'll equal H3O. Notice, just look at the algebra here. We're going to divide both sides by hydroxide, and that equals the KW divided by hydroxide. And that's equal to H3O. So if you pull out your calculator, go ahead and solve this, and make sure you type this in your calculator with parentheses in the denominator, because your calculator takes the multiplication symbol as a separate order of operation. So if you don't have parentheses, it messes the answer up. So pause and see if you can get the correct answer here. All right, so the answer is 7.1 times 10 to the negative 4 molarity, and that is the H3O plus concentration in this solution. All right, let's do another problem. Write the dissociation reaction for HCl in water. All right, so we need to dissociate HCl in water. There's two ways we could do this. We can just take HCl and split it up. We've got a chloride ion and we have a hydrogen ion. But you could also write this including the water molecule, because dissociation in water means, well, it's in water. So we can include the water molecule, and the acid is going to transfer hydrogen to the water molecule. So we're left with chloride ion and H3O plus. Either one of these is acceptable for the dissociation of an acid. You can either include the water molecule or not include the water molecule. Also, this hydrogen ion written as H plus, as well as the H3O plus, either of those are interchangeable and they mean the same thing. It's the hydrogen from the acid. In reality, the hydrogen doesn't just float off by itself in the solution. It in fact does attach itself to a water molecule. So you can say that this second reaction here is a little bit better representation of what's happening, but the first is also perfectly acceptable. And even on the AP Chem exam, both of these are acceptable. All right, so then the second part says, if 2 moles of HCl is dissolved in 1.5 liters of water, what is the concentration of the H3O and OH in the solution? Well, first let's find the concentration of HCl. Concentration is moles divided by liters. We have 2 moles of HCl and we've got 1.5 liters. That is 1.33 molarity of HCl. Now remember, from our chemical reaction, the H plus is equal to H3O, and also this is a completion reaction, so all of the HCl turns into these products. So therefore, whatever concentration you have of HCl, you also have of H plus, or you could write it as H3O. So this is the first part of the question, or first part of the answer. What is the concentration of H3O? But then we're also asking for hydroxide. Now you might be wondering, where is the hydroxide? We don't have hydroxide in this problem. Well, there's always a little bit of hydroxide in every solution. So, we can take Kw is equal to H3O plus times OH minus. The Kw is 1.0 times 10 to the negative 14. We have the H3O as 1.33, so divide both sides by that, and then we get to solve for hydroxide. Pause to see if you can calculate this. The answer is 7.5 times 10 to the negative 15 molarity hydroxide. And there's the answer. All right, let's look at some more dissociation reactions. So when we are dissociating a acid, you can either include the water molecule or not. So here's the hydrobromic acid without the water molecule, and here's hydrobromic acid dissociating with the water molecule. Either way, what's happening in the solution is the same thing, and either of these representations is an accurate way of writing it. Here's just an example of a dissociation reaction where the acid is made with a polyatomic ion, nitrate. So HNO3 dissociates into NO3 minus and H3O plus. When you have to write a dissociation reaction for bases, we're going to leave the water molecule out when you have a base made with hydroxide. So you just take lithium hydroxide, a strong base, and you turn it into lithium ion and OH minus. You just break it apart, dissociate it. Remember that if you have a base that is made with a cation with a 2+ charge, like calcium, the chemical formula is CaOH with a 2 on the outside of the parentheses. So that turns into 1 calcium ion and 2 hydroxide ions. So just remember that this coefficient, or this subscript turns into this coefficient because we have 2 hydroxides for every 1 calcium hydroxide. Now, when you're dissociating a base or writing out the dissociation reaction for a base that does not have hydroxide in it, like NH3, then you write out the water molecule so that you can take the hydrogen from the water molecule and move it over to the base, because that's what bases do. They accept a hydrogen, and then it would look like NH4 plus and OH minus. All right, so remember we have these reactions. These are on the back of your periodic table. Kw is equal to H3O plus times OH minus, and Kw is always equal to 1 times 10 to the negative 14 at 25 degrees Celsius, but all of the problems we are working with are at 25 degrees Celsius. H3O plus is named hydronium or hydrogen ion, and we could also write this as H plus. So H plus is equal to H3O plus, and either of them have these names. Hydroxide is the OH minus. All right, from your problem set, here's problem 1 from 14.2. What is the hydroxide ion concentration with a hydronium concentration of 6.8 times 10 to the negative 10 molarity or moles per liter? Pause to see if you can work this out. Remember that hydroxide is OH minus, and when it says concentration, that means in brackets, which means molarity. So we're looking for the hydroxide ion concentration. We're given the hydronium ion concentration as 6.80 times 10 to the negative 10 molarity, which is what moles per liter is. And here is the answer. Problem 2 from the 14.2 problem set. What is the H3O plus concentration in a solution with the hydroxide minus concentration of 5.67 times 10 to the negative 3 moles per liter? Pause to see if you can work this out. And here is the answer.